What if the future of energy isn't in the sun, the wind, or the waves, but lies in the tiniest particles known to mankind? As we look towards the limitless sky or the vast ocean, it's easy to imagine harnessing their power to fuel our ever-increasing energy needs. However, the intermittent nature of these sources, their geographical limitations, and the massive infrastructure required to harness them present significant challenges. Enter quantum fusion energy. This revolutionary concept proposes that the key to our energy future might be hidden in the smallest particles of the universe. By controlling fusion reactions at the quantum level, we could potentially unlock a source of power that is clean, safe, and virtually inexhaustible. Central to this concept is the McGinty Equation. This equation is a crucial tool in our quest to optimize plasma confinement and control, thereby advancing nuclear fusion research. Now you may ask, what's this McGinty equation and why is it so important to quantum fusion energy? Let's find out. The McGinty equation might sound intimidating, but it's quite straightforward when broken down. Let's start by looking at the first part of the equation, P's xt, equal sign P's QFT xt. This represents the solution of free quantum field theory. But what does that mean exactly? Well, imagine a vast open field. This field isn't just any ordinary field, it's a quantum field. Now in this quantum field, particles are not like solid balls bouncing around. Instead, they're more like ripples or waves spreading out across the field. This is the quantum field theory part of our equation, represented by PSQFT xt. The x and t in the equation stand for space and time respectively. So when we say PSXT, we're referring to the state of the quantum field at a specific point in space and a specific moment in time. The psi is a wave function. In quantum mechanics, wave functions describe the quantum state of a system, and they play a crucial role in the Schrödinger equation, which is a fundamental equation in quantum mechanics. So, PSQFT xt in our McGinty equation is essentially describing the quantum state of our theoretical field at a particular point in space and time. To make this even simpler, think of PSQFT xt as a snapshot. Just like a photograph can capture a specific moment at a specific place, PSQFT xt captures the state of the quantum field at a given point in space and time. But of course, the quantum field isn't static, it's dynamic and constantly changing. So our snapshot PSQFT xt is just one frame in a never-ending quantum movie. In essence, the first part of the McGinty equation is all about understanding these quantum snapshots and how they change over time and space in our theoretical field. That's half the equation. Now let's move on to the fractal part. In the second part of the equation, we delve into the realm of fractals. Now you might be wondering, what is a fractal? In layman's terms, a fractal is a pattern that keeps repeating itself on smaller and smaller scales. It's like a Russian nesting doll. Open it up, and there's a smaller doll inside. Open that one, and there's an even smaller one, and so on. This concept of self-similarity is key in understanding the second part of the McGinty equation, fractal. This term represents the fractal structure of quantum systems. Remember, quantum systems can be thought of as tiny, subatomic Russian dolls, with particles nested within particles, each layer reflecting a smaller scale of the same pattern. The parameters in this part of the equation, namely d, m, q, and s, characterize the nature of these fractal patterns. For instance, d could represent the dimension of the fractal pattern, m might denote the mass of the quantum particles involved, and q and s could be parameters that describe the specific characteristics of the fractal pattern. The beauty of the fractal term in the McGinty equation is that it allows us to use integral calculus, Laplace transform, and the convolution theorem to derive the fractal correction term. In other words, it gives us a mathematical tool to decode the self-similar patterns in quantum systems. This understanding of the fractal nature of quantum systems is crucial when it comes to optimizing plasma confinement and control in nuclear fusion research. By understanding the fractal patterns in quantum systems, we can better predict and control the behavior of plasma, the hot soup of particles involved in fusion reactions. With that, we've broken down the entire McGinty equation. But how does this relate to quantum fusion energy? The McGinty equation plays a pivotal role in our understanding and control of quantum fusion energy. It's a formula that may seem daunting at first glance, but its implications are monumental. Let's delve into how it works. The equation is written as P's xt equal sign PSQFT xt plus P's fractal xt dmqs, where PSQFT xt represents the solution of the free quantum field theory, and P's fractal xt dmqs refers to mechanical systems. It's this second part of the equation that helps us optimize plasma confinement and control. which are essential for harnessing quantum fusion energy. Plasma confinement involves keeping a cloud of superheated particles within a controlled space. The McGinty Equation, with its fractal term, provides a mathematical framework for understanding the chaotic behavior of this plasma cloud. This understanding allows us to control and manipulate it more effectively. But what's the end goal here? Why are we striving to control this superheated plasma? The answer lies in the promise of quantum fusion energy. Quantum-controlled fusion reactions have the potential to revolutionize our energy landscape. Imagine a world where energy is not only clean, but virtually limitless. This isn't a fantasy, it's a real possibility, thanks to the principles of quantum fusion and the guidance provided by the McGinty Equation. In fact, the equation has a second variant, P's xt equals sign P's qft xt plus P's fractal xt dmqs plus P's gravity xtg. This extended version allows us to consider the effects of gravity on the quantum field, giving us an even more comprehensive understanding of the conditions required for successful fusion reactions. So, the McGinty Equation is more than just a string of symbols. It's a key to a future of clean and abundant energy. It's a testament to the power of human ingenuity and our relentless pursuit of knowledge. And it's a beacon of hope for a world that's increasingly conscious of its energy consumption and the need for sustainable solutions.